So my name is Ryan Nienhuis. I'm a technical product manager for Amazon Kinesis. Today we're going to be talking about building a streaming data platform on AWS. We have one of our longtime customers, Ram, with us, who's one of the co-founders of Beeswax. And I'm really excited about this presentation because they helped us build the platform. So the feedback that they provided directly impacted the features that we worked on, and they really evolved with the service. So Amazon Kinesis Streams has been out for 3 years, and we'll go into the services that Amazon provides. But their feedback definitely impacted how we built and what we built over the last couple years. So what are we going to cover today? We're going to go over, this is an expert level talk, but we'll cover some introductory material for those of you who don't have context, just so you can ramp up on what is Amazon Kinesis. I'll mention some best practices and key considerations for each part of a streaming data platform on AWS. So streaming data ingest, data processing, and sort of end-to-end best practices. And then after that, I'll transition to Ram, who's going to go over what Beeswax does as a business and how they use streaming data and real-time data to differentiate themselves from their competitors and how they built that service on AWS. So before we get started, let's just, by a show of hands, who has used a streaming data product before? It doesn't have to be Amazon Kinesis. Who is currently using Amazon Kinesis? Great. What I love to see is every year we give presentations, we see more and more hands. So a lot of the best practices that we have are generally applicable whether you're using Apache Kafka or Kinesis Streams or even some queuing technologies. So you'll get something out of it whether or not you're a customer. But if you've never used Amazon Kinesis, this will be a good introduction into the types of challenges customers have when they implement an end-to-end streaming data solution on AWS. So I like to start out just off the premise, what is streaming data? Because everyone has a different definition, and ours is intentionally vague. It's an unbounded sequence of events that is continuously captured and processed with low latency. I think the most important aspect of this is continuous. So the data is moving through a set of services to an eventual destination, and that destination could be a database, it could be Amazon S3, it could be storage, it could be real-time alarms and event notifications through your operational monitoring solutions. The key aspect of it is that data is continuously generated, you're continuously capturing it, and continuously reacting to the data and delivering it in real time to an eventual destination. So Amazon Kinesis is made up of 3 services: Amazon Kinesis Streams, Amazon Kinesis Firehose, and Kinesis Analytics. And from left to right is sort of the order in which we released the 3 services. Kinesis Streams was the first product that we released. It's in every single AWS region except for GovCloud, which will be very soon. And then it's sort of like a core infrastructure service. It's what we'll be talking about most today. You write data to a Kinesis stream and read data off of a Kinesis stream through a custom application that you build yourself. Kinesis Firehose takes the #1 use case for streaming data, and that's capture and aggregation and persist to a destination, and makes it super easy to use through UI, some basic configurations. We have some exciting features coming up in the next couple of weeks for that. Kinesis Analytics we launched 3 months ago at the New York City Summit, and it allows you to write standard SQL over streaming data sources such as Kinesis Streams and Firehose. What it does is it basically presents what almost looks like a relational table on top of your stream for you to query against and do things like real-time alarms and notifications, time series analytics, or feeding a real-time dashboard. So Amazon Kinesis Streams. So the primary value proposition for Kinesis Streams is that it's very easy to get started. You can choose the framework of your choice, be it Spark Streaming, Apache Storm, or we ship our own libraries like the Kinesis Client Library. But the big emphasis is it's easy to use, but it gives you that flexibility at a fairly low cost. Kinesis Firehose, it is 0 or very, very little administration. The only thing you really have to worry about is making sure that your IAM configuration is correct between your stream or your Firehose delivery stream and your destination, and then just writing data at any rate. We scale the stream for you. There's no concept of harder to comprehend aspects like shards or partitions. And it just gets the data in as quick as a minute, sometimes lower, to the destination of your choice. It's very fire and forget. We're not going to talk about Firehose too much today, but the one thing I will say is a lot of customers use streams and Firehose for different use cases or in conjunction. So it's very common to take data written into a stream and also write it to a Firehose, or attach an application that's just forwarding it to a Firehose to get it to those destinations. So Kinesis Analytics allows you to build real-time applications using SQL. You basically define a source configuration and a schema associated with it. Your application code, which is a set of SQL queries that you can run in parallel or serial on that streaming data source. And then a destination, or a set of destinations in which you want to emit your metrics. Very common use cases are, I want to compute averages, mins, maxes over a 1-minute period and emit the data to Redshift, or emit the data to my MySQL database. Another very common use case for it is doing message-based filtering. So I'm looking for something using a very simple where clause, and then emitting it for eventing or alarming. But it also supports advanced use cases. So we have some machine learning algorithms built into it. One of them is an anomaly detection algorithm that will detect anomalies on your stream, and it's exposed to you through a simple standard SQL function. So the bulk of this presentation is going to be about Amazon Kinesis streams. So I'm going to go into some best practices about working with the service, and I'll provide some context of just high level about what the APIs are. So this is a typical, very architecture diagram for Kinesis streams. You've got a set of data producers writing to a stream, and then a number of data consumers reading off of the stream to power different use cases. And if you go from the top to the bottom of those data consumers, you really see what we see typical customers do in their evolution of implementing streaming data use cases. They start with simple use cases like aggregation, deduplication, and persisting to Amazon S3 for either later analysis and batch analytics tools or just archival. And they progress to more sophisticated use cases like machine learning. The key concept in Kinesis is a stream. You provision a stream by creating it, specifying the name and a number of shards. And that's sort of our unit of scalability, and it's also our unit of parallelism. So if you need 10 megabytes per second, you create a stream with 10 shards. If you need 100 megabytes per second, you can scale your stream up through very simple APIs by just putting 100, and we'll scale you up to 100 shards. Another note on this slide is that the variety of data producers. So there are several different approaches that we'll talk about in the presentation about how people use streams. So some customers will logically separate their data into separate streams. So they'll have their application logs going to one stream, their clickstream data going to another stream, their operational metrics going to a third stream. Other customers use a single big ingestion pipeline, and there's pros and cons associated with that. But the point is that there's a lot of people use Kinesis streams and other streaming technologies to ingest a very large variety of data, and that's really one aspect of big data where streaming data is focused on, is a variety of data. So a Kinesis stream, I mentioned streams are made of shard, and it's our unit of parallelism and throughput. So each shard gets you 1 megabyte per second in, or 1,000 records per second in, so write, 2 megabytes per second out, and 5 reads per second out. So, and a read will give you a batch or a bunch of records to read off of it. Data is stored in a stream as a temporal buffer. So it's configurable, by default it's 1 day. It's configurable up to 7 days. And you scale a shard by splitting and merging shards, but these are the two APIs we launched with. We recently launched a new API where you just choose the number of shards to scale to, and we'll scale you up to the number of shards. And we'll maintain the lineage of the shards, which for processing locality, which I'll get into in a couple of slides, is very important. This is a very top feature request from customers because they wanted an easy way of just, while the stream is live, while you're writing to it, while you're reading from it, without any downtime, can I please just scale from n number of shards to m number of shards very quickly. So we had a library that still does it. It's still one of the most popular libraries on GitHub. It's called Kinesis Scaling Utils. But the customers use that library to scale their streams up and down because it called these split and merge APIs under the covers. But recently, 2 weeks ago, we released an API. You just go to the console, enter the number of shards you want to scale to, and it scales you very, very quickly, typically in seconds, sometimes in minutes, depending on how large the stream is, with very little thought or complexity on your end. So how do you write data to a Kinesis stream? So we have two APIs, put record, which is an individual record, and put records. Each record can be up to 1 megabyte in size, right? The put records or the batch put mechanism is typically used on data producers that are very large. So I have a super large EC2 instance that's producing 1 megabyte per second of logs, so pretty extreme. Or another use case is that a lot of customers, and Ram will go into this because they implement this use case, they have a buffering fleet or a fleet that's sole job is to basically get the data and then write data to the Kinesis stream. In that case, using put records gives you a higher throughput API. When you write data, you specify a blob of data, the stream name, and a partition key. The partition key determines which shard the data record will be stored in. We take that record and we put it through a very simple MD5 hash, and then it just ends up on in that shard. Choosing a partition key is very important. Most of our customers choose a random number, all right? Just so that the traffic is evenly distributed across all shards in the stream. However, there are customers that need processing locality, so meaning that they need all records associating with a particular logical identifier are sent to the same thread that's processing it, right? This is for streaming MapReduce use cases. If you're trying to aggregate events on a specific, say if you're using an EC2 instance ID, trying to aggregate events on that specific EC2 instance, you need to use a logical ID. The key is, though, is that you want a very high cardinality between number of keys and number of shards. So 100 to 1, 1,000 to 1, 10,000 to 1. So very, very high cardinality. Because this makes it more likely that traffic is evenly distributed through your stream. An example of a bad partition key would be, I'm a service, I have 10 customers, one customer is 50x larger than the other 9. So, and I'm putting all that throughput to a single shard. That's an example of a bad key. There's low cardinality between the keys and shards, as well as one of the keys has a lot more throughput than the other keys. For options of interacting with the APIs, very few people actually interact directly with the APIs. It is done, but a lot of people use one of our agents. We have the Kinesis producer library, which is meant for very high throughput producers, like those big EC2 instances I was mentioning. We have the Kinesis agent, which just tails a log file and writes data to the Kinesis stream or Firehose. But we also have open source projects with FluentD, Flume, and a lot of other tools. Choose the solution that meets your use case that your developers are most comfortable with. Because as I mentioned, those data producers, there's a lot of variety of them. We have a lot of options for you because of that. So key considerations with data producers. So almost all data producers are stateless, and they're typically not very reliable. Like, they can go down for any reason. And an example is an IoT sensor or a mobile device or a web browser. So you need them to get data off of those machines very, very quickly and very, very efficiently. The other addition to this, you get some benefit in cost as well as some benefit in efficiency by buffering a small amount of time. So for example, instead of writing every single event to the stream, waiting 100 milliseconds or 50 milliseconds or 10 milliseconds to buffer records for a very small period of time before you write using that put records API or a batch put. So there's writing data to the stream, there's also reading data to the stream. The mechanism to read data from the stream is basically call an API to define where you want to read, and this is called getShardIterator, and then start iterating using get records and continuously reading data from the stream. You can call getShardIterator from the oldest data in the stream, from the latest data in the stream, or we have time indexes. You can say, I want to start reading from an hour ago, 2 hours ago. 99% of use cases are reading from the tip or reading from the latest data in the stream. And then most customers have some replay scenario where they want to go back a couple hours for a particular set of data, maybe processing failed or their processing logic did not work as expected, they need to reprocess data. A key point on this slide is I've mentioned processing locality a couple times. So increasing number of shards will both increase throughput as well as make your processing scale more because you're increasing parallelism, but you lose processing locality the more shards that you add. So the example that I gave earlier about an instance ID, if you need to correlate across multiple partition keys, you lose that as you scale up. Again, there's a lot of options to read data off of the stream, but almost all of them use the Kinesis client library in some way or another, which is the number one thing to read data off of a Kinesis stream. And it's both our low-level and high-level API for consuming records off the stream. It handles things like lease management, load balancing, and allows you to focus on just the record processing logic. So there's two key components to it. There's the worker. The worker is one worker per one JVM, and then one record processor for one shard. It also provides a lot of monitoring for you, and this is key to diagnosing issues. We find that a lot of people don't look at this monitoring until they run into an operational issue, but when they do, they're happy that it's there. The most important metric that the KCL emits is a per application, per shard, millis behind latest metric. It just means how far behind the stream I am. Am I keeping up with every partition that I'm reading from the stream? So when we talk to customers about what to do from an operational context, the most important thing is set an alarm on that metric. You can set it at the stream level or you can set it at the shard level, but it basically tells you whether my stream is healthy, whether my consuming app is healthy or not, whether I'm keeping up with data in the stream, whether I'm reading the latest data. Often we find a lot of customers don't test scale before they go into production. I don't know why this is, but it happens very often where their record processing logic doesn't scale linearly with the amount of throughput, and it's a very easy test. So you just need to test your record processing logic scales with up to 1 megabyte per second. It can be done locally on a developer's desktop. Do it before you go into production. All right? It is extremely easy test to do. And the reason why I'm suggesting do is because a lot of customers, they might be utilizing their shards at 10% or 20% when they first go into production. And as their throughput scales, or they get a huge influx in traffic by some event coming in, and then all of a sudden they're utilizing their shard to 80%, and their processing isn't scaling linearly. And this is an easy test they could have implemented from the very beginning, which would save them a lot of time. And the other thing I'll mention in this slide is replay. So have a retry strategy. There are several different strategies to implement. The most common one is, since we offer a time index, just if you fail processing or if the downstream destination is down or something, other errors happen with your stream, have a strategy to dynamically update your application to start reading from the specific point in time where this event occurred, which the KCL supports. Another strategy is to just bounce your application with the time that you want to start reading or reprocessing. Another strategy is to use historical or batch-based processing on Amazon S3. The point is, there's a lot of different options here. Just make sure that you think about this before you go to production. So this is my last slide, and this is before I pass it off to Ram. And this is just key considerations to talk about for the end-to-end streaming data solution. Most customers are successful by implementing the simplest use case possible. In that first slide I presented on Amazon Kinesis Stream's key concepts, this was aggregation and deduping, and then writing it to S3. So if you haven't used the streaming technology before, we recommend you start with the simple one first, and you'll run that app forever. The number one app for running, even if as you progress to more sophisticated use cases, is streaming data archival, because it allows that replay scenario if anything goes wrong. And even if you move on to more sophisticated use cases, most customers will always have that app running. Being able to support the variety of data that comes through is something you need to think about as well. There are two different strategies that we generally see. One is to do so in any sort of central way, where you have a schema registry, a consumer app calls an API, reads the schema down, and then processes the record based off of that schema registry. It's one approach that works if you want tight data management across your organization. However, if you want to give flexibility to individual developers, A lot of people will just do so locally and force any consumer that they attach to a stream, it's their responsibility to handle the different data formats. It allows you that flexibility, but also introduces some problems if, say, someone developing your mobile app pushes a schema change and your record processing logic can't handle it. So there's some cost to that flexibility. Integration. So there will be either internal or external customers that are going to depend on this data arriving and depend on it with certain SLAs. It could be you're giving them once a day you're updating a MySQL database, or it could be once a second you're updating Amazon S3 with new data. Understand those guarantees and understand where to apply back pressure if necessary. So what do you do if that destination is down? What do you do if there's something wrong with your end-to-end streaming data pipeline? Make sure that you understand the guarantees you're offering both the internal and external customers. And then the last point, I mentioned this a little bit previously, but determine whether you want to use multiple consumers or one monolithic application. Ram will go into their choice of using one monolithic application, and both have advantages and disadvantages. If you have a lot of changes to various use cases very frequently, there's a disadvantage for using one monolithic application. But it allows you to implement all of your use cases at the cheapest possible cost, because you have these processing frameworks. Each of them is going to take a certain amount of compute. Attaching additional instances means reading more from the stream and processing it. Thank you guys very much. I'm really excited about the next part of the presentation. And with that, I'll pass it off to Ram.
Thanks, Ryan. Good afternoon. I'm Ram, CTO of Beeswax. And today I wanted to share with you our experiences of building a streaming application on top of Kinesis. So before we get started, a quick introduction to Beeswax. This is a company that I started with two of my former colleagues from Google. We started the company in 2014. It's based out of New York. And our first product was released in summer of 2015. It's called Beeswax Bidder as a Service. I'll talk more about Bidder as a Service in my following slides. We just recently closed our A round and are now really looking to grow our team, business, and infrastructure. And so if you're interested in working on really large-scale, high-performance distributed systems, DevOps on AWS, or machine learning, feel free to reach out to me after this talk, or please go check out our website. So what we do at Beeswax is real-time bidding. Now, the programmatic digital advertising these days is transacted on these really large online marketplaces called ad exchanges. Ad exchanges bring together publishers and advertisers. Publishers are sellers on this marketplace. They are selling placements. A placement is a place where you can show an ad. And the advertisers are buyers. They're buying this placement in order to show an ad. A transaction on this exchange is initiated whenever a user visits a website or uses an app that sends an ad request to the exchange. This ad request will contain some information about the placement, such as the name of the app or the domain of the site, along with the information about the user ID, such as the cookie or the mobile device identifier. And the exchange receives this and then broadcasts it to a set of bidders. Now, a bidder is a piece of software that's deployed on behalf of an advertiser to help them execute their advertising campaigns. And the bidder responds back with a bid price and the markup of the ad. And then the exchange waits to get back the responses from all the different bidders, runs a second price auction, picks a winner, and the winner's ad gets shown to the user. So this is what happens behind the scenes every time you see an ad on a website. And this whole transaction lasts for less than 200 milliseconds, and it's done many million times per second. And the industry term for the process that I just described is real-time bidding. Now, it turns out that building a bidder is a really hard technical problem. So for advertising campaigns to be successful, they need to reach a really large audience. And often, this audience is located in different parts of the world, such as North America, Europe, Asia, etc. And so a bidder has to be able to scale up to receive and process at least 1 million queries per second in order to be able to find the users that are relevant for a particular campaign. Furthermore, the bidder has to be deployed in different regions, such as US East, US West, EU West, and the state amongst these different deployments has to be carefully coordinated. And so building such a large-scale distributed system is really hard, and operating it is an even harder challenge. And in terms of performance, as I mentioned, an ad transaction on the exchange lasts for only 200 milliseconds, and out of that, the exchanges set a timeout of 100 milliseconds to the bidder, within which they expect to get back a response. In reality, the bidders only get 20 milliseconds to process a request because a large fraction of the time is spent in round trip over the internet. So building a bidder requires aggressive optimization, which is again a non-trivial engineering task. And finally, bidders operate in a complex ecosystem where they are plugged into multiple supply vendors, data vendors that provide signals for viewability, fraud detection, et cetera. And putting together all of this it requires a lot of domain expertise. And so for the reasons that I just described, building a bidder is a really hard problem. So advertisers that wish to embrace RTB currently have two options. They could go ahead and build their own bidder, but it's a very risky investment of time and money. The other option is to use this software called demand-side platform, or DSPs. A DSP is like an online broker in a financial marketplace. The good part of using a DSP is that it just works. However, it provides very limited opportunities for customization. And so now, with the Beeswax Bidder as a service, the advertisers that wish to use RTB have a third option. Beeswax Bidder as a service is a fully managed ad tech platform built on top of AWS. We are already integrated into all the supply sources and the third-party data vendors. We provide a rich set of features such as campaign management, budgeting, frequency capping, reporting, targeting, et cetera. And we also provide optimization features in the form of pacing and click prediction. So by using this platform, a customer can get up and running with their campaigns as they get access to a full-feature UI. It's basically a DSP on day zero. However, the real power of the platform lies in the rich set of APIs that we provide that really enable our customers to build custom bidding solutions on top of this. So for example, we provide an augmentation API that lets our customers augment a bid request with their own signal. They can bring their own data. So an example of this could be, for example, if there's a customer that has rich location data, they can look up the latitude and the longitude in the request and then augment the request with where the user is present and then target ads to them based on that. Similarly, we provide a bidding API that lets advertisers choose a creative and also a bid price on a per request basis. And this is, again, a level of flexibility that is not supported by any DSP. So for example, a big online retailer could use this product and then recommend products out of their inventory as they see the users around the web. So really, the focus here is on the advertiser to sort of build the differentiated aspect of the bidder by bringing their own data, their own strategy, and leaving the non-differentiated aspects of like integration to supply sources, scaling, et cetera, to Beeswax. So with this introduction to Beeswax and RTB, in the rest of the talk, I'll cover the system architecture, go over the reasons for why we chose Kinesis, and then talk about some of the challenges that we faced while building our application, and then discuss some of the trade-offs that we had to evaluate to arrive at the solution. So the following is a stream-centric view of our application. So on the left, we have the data producers. The bid data producer is a set of servers that are deployed on AWS EC2 autoscale groups, and they receive and process millions of queries per second from the different ad exchanges. The real challenge for us in implementing the bid data producers was to be able to scale up data collection to such a high volume. The impression and the click data producers receive events from low QPS sources, such as notifications of a win from an exchange, or when a user clicks on an ad, all those events from the browser end up with this data producer. The challenge with this data producer was to be able to perform lossless data collection. All the producers log the events that they receive into a common event stream, and we use protocol buffers for encoding the payload of the event itself. The core of our architecture is this application called the Streaming Message Hub that is responsible for reading events from the stream and processing them. We expose a REST API to our customers that lets them program the Streaming Message Hub so as to be able to aggregate, transform, and then deliver records to a destination of their choice. We currently support delivery to S3 buckets, Kinesis streams, data warehouse solutions such as Redshift, or also a real-time HTTP post to a server that they might have deployed. So now I want to go over the reasons for why we choose Kinesis. So the infrastructure requirements were really motivated by RTB use cases. So we clearly needed to support ingestion at a very large scale. Also, we needed an infrastructure that we could depend upon for reliable storage, as well as being able to deliver events with low latency. And finally, we also needed to rely upon sequence retrieval of events, and I'll talk more about this when I talk about event joins in my later part of the talk. And so it's possible, theoretically, that we could have avoided streaming altogether and build this on top of S3. But that would have been a really bad design choice because we would have ended up with a large number of really small files in S3 that we would have had to manage ourselves in order to minimize latency. And furthermore, it's not really clear how we could have built sequence retrieval with files, raw files on S3. So at the time when we were building this system, we really had a couple of choices on AWS. We could choose Kinesis, or we could roll our own Apache Kafka cluster on Autoscale EC2. In the end, we decided to choose Kinesis mainly because it's a service that's fully managed by AWS. And I cannot emphasize this aspect enough, particularly for small engineering teams such as ours, because Kinesis does a really good job of replicating data to multiple availability zones and makes the data available. And trying to do this ourselves and meeting that level, like the operational overhead of trying to do this ourselves and like meeting this level of reliability is something that we just simply could not have afforded to do. Also, based on our early sort of communication with the team and reading the documentation, et cetera, it was pretty clear that the infrastructure could scale to meet the requirements of RTB. And also, finally, the pricing model of Kinesis offered us with a lot of opportunities to perform cost optimizations. So really, in the end, it wasn't that difficult a choice for us to make for going ahead with Kinesis. So now I'd like to talk about some of the challenges that we faced in building our application. So one of the features that we provide in our platform is a listening bidder. A listening bidder is a bidder that doesn't actually bid, but instead is only interested in listening to a filtered stream of bid requests. The filtering criteria itself can be specified as a Boolean expression on the attributes of the bid request. And really for us, the main challenge here was to be able to build a data producer that can collect events at a very high scale, while also making sure that the costs are managed. And now I want to cover some of the optimizations that we performed in the design of our producers in order to implement features such as the listening bidder. So one of the dimensions of the Kinesis pricing model is the number of put payloads that are uploaded into the stream. Put payload is a 25 kilobyte chunk of data. So in order to minimize cost, it made sense for us to pack more of the records, the bid requests, into a single put payload and upload it. However, this reduces the reliability of the application because now it's vulnerable to data loss. In case the producer crashes before it gets a chance to persist, then you end up with a situation where you've lost some data. Unfortunately, I don't think that there is an inexpensive way to perform reliable data collection at scale. However, for some of our low QPS producers, we were able to come up with a few creative things. And I'd like to share one of them with you. So for the low QPS data producers that we have, we front them with an Amazon load balancer, an ELB. And ELB has this feature called request logging that actually logs the URL of the GET request and makes it available on S3 a few minutes later. So keep in mind that this is not streaming data from ELB, but it's actually data that's batched, put into files, and then made available. So in the event of a data loss, what we do, we have a mechanism in place to replay these logs from S3 and re-ingest data, sort of inject data into the stream. This enables us to perform lossless, zero loss collection. And I also want to point out that this is only possible if the attributes of your event could be encoded within the URL of a GET request to ELB. So my point is that there could be many interesting ways to sort of work around some limitations. Also, while performing optimizations, it's important to consider the overall system cost. So compression, for example, reduces the amount of data that's put into the stream, thereby reducing the infrastructure costs of Kinesis. However, compression obviously also increases the CPU utilization of the producers and the consumers. So it's really important to experiment and make sure that if whether compression makes sense and what compression technology to use. So in our experiments, we found that using Snappy instead of gzip actually resulted in a reduction of our overall cost, even though Snappy has a lower compression ratio as compared to gzip. So it's really important, again, to just keep the overall system cost in mind. Buffering of data obviously leads to an increase in throughput because more data can be uploaded per API call. However, it increases latency because data is being buffered, but a simple workaround for that is to periodically flush your buffers so as to have a cap on the latency. And finally, as Ryan mentioned in his talk, it's really important to choose the right partition key. And it's particularly important to choose a partition key, I feel, that's uniformly distributed over the shards if your application permits. And in sort of the scenarios such as ours, where we're doing data collection at a really large scale, it becomes particularly important because you don't want to end up with a situation where a single shard becomes a hotspot and a single point of failure. And in our application, we choose the auction ID of the incoming bid request as the partition key. And as I'll talk about it later, it also is a sort of a join key between correlated events in our stream. The second challenge that we had to address was of data transformation and fan-out. So the Beeswax platform produces a continuous stream of data that needs to be constantly fed to our customers so that they could build their own strategies. And so we provide an API to our customers that lets them configure both the format of the data as well as the destination where they'd like to receive it. And this really enables them to ingest data more easily into their systems. And so the main challenge for us here was to architect a config-driven system that can determine the format, the schema, and the destination of every record. And also, from a production standpoint, we wanted to make sure that our deployments were elastically scalable based on the number of events in the Kinesis stream. So our solution, called the Streaming Message Hub, is built on top of KCL. As Ryan mentioned, KCL already handles load balancing as well as stream checkpointing. Also, it uses DynamoDB under the hood to store some of its state. However, the DynamoDB resource utilization is very minimal. It doesn't really add a lot to the overall cost. And it provides this abstraction called record processor, which is mapped to every single shard in the stream. And so, if you're building scalable reader applications, KCL is the right place to start. Unless there is something esoteric about the application, I really cannot imagine a good reason for not using KCL. So in our application, the KCL record processor receives a batch of records, it uncompresses it, and then does unparsing on the serially encoded binary protocol buffer data. At this point, we know the type of the event that we're handling. It could be a bid event, a win event, or a click event. And then based on the type of the event, we route it to the appropriate adapter. The job of the adapter is to perform schema or format transformations, and it's again driven by the customer config, whatever they want, and they told us through the API. Once the adapter is done transforming the records, it is sent to a string of emitters. The job of the emitter is to, again, copy the records based on the configs and copy them into an in-memory data buffer, and then periodically flush this data buffer to wherever it's trying to persist the data. And so we currently support emitters for S3, Kinesis, HTTP, endpoints, et cetera. And we buffer and flush so as to increase throughput. And also, one of the key aspects of the application is that it checkpoints data only after an emitter has successfully delivered the data to the destination. And by doing this, we are able to guarantee at least one semantics, which means that we'll process every record in the stream at least once. Also, since this application is deployed on an autoscale EC2 group, we were also able to achieve our goal of having an elastically scalable deployment, because we make use of CPU utilization alarms from CloudWatch to scale up and scale down our fleet. So now I want to go over some of the trade-offs that we considered in the design of the streaming message hub. We went ahead with a design where we have a single reader for every combination of format and destination, as opposed to having multiple readers. Having multiple readers obviously increases the fault tolerance of the system. There's no more a single point of failure. However, in our application, it turned out that the CPU cost of uncompressing and unparsing protocol buffers was pretty significant, and we really couldn't justify paying the cost for it multiple times in different readers. Also, the goal of having a scalable, elastically scalable compute fleet could have been realized using Lambda as opposed to EC2 autoscale. The advantage of using Lambda is that it's managed by AWS. However, we recently moved to using Spot instances, which significantly cut down the cost of this self-managed solution. And also the rich set of metrics that are provided by KCL and Kinesis Stream really made the task of monitoring and operating the service a whole lot simpler. So in the end, we really couldn't justify the cost overhead of moving to Lambda. But then again, this is something that really depends on the application. And as Ryan mentioned in his presentation, Kinesis Firehose is another service that we considered. And this was very early on when Firehose was just announced. And at the time when we were looking at Firehose, it did not support record-level fan-out of data to multiple destinations, and also sort of arbitrary data transformation. As I mentioned, we have protocol buffer as the data format in our stream, and there was no easy way for us to convert from protobufs to something else using Firehose. But then based on feedback from us, and I'm sure other customers, the team is coming up with a bunch of new interesting features, at which point I think it would be a very interesting alternative over a self-managed EC2 solution. The final, the other aspect that I wanted to touch upon is operating the streaming message hub. So in terms of scale, we are currently operating with more than 300 shards in a given region and consuming about 250 megabytes per second. We make use of the CloudWatch alarms on metrics that the Kinesis streams directly export. So the Kinesis capacity alert is set up in our system to trigger whenever the number of bytes in the stream reaches 80% of the overall capacity of the stream. And whenever this alert fires, what we do is go ahead and manually reshard the stream using the Kinesis scaling utils that Ryan mentioned. However, there is a new API that was recently introduced, and by making use of the API, the actions that we perform when this alarm fires can be completely automated. The other alert that we pay a lot of attention to is how many seconds behind real time is the current iterator. And if this goes behind 20 seconds, for instance, we raise an alarm. This alarm is pretty critical for us in order to maintain our latency SLAs with our customers. And usually when this alarm fires, it means that there's a problem in the reader application that requires immediate triage. In terms of overhead of management, I would say we roughly receive about 2 alarms in a month, and most of the times it's the capacity alert because our service is growing and therefore we're basically running out of capacity on the stream. The final challenge that I want to talk about is joining streams. Now, joining refers to putting together correlated events into a single record. And this is a high-level service that we wanted to provide to our customers so that they don't have to do the join themselves, and they could directly consume this join data to feed into their ETL pipelines or their machine learning systems. And there are a lot of challenges in implementing joins correctly. So with joins, you have to support exactly once semantics. Now, as you may recall, that in our producer, in order to guarantee lossless collection, sometimes you end up replaying data and re-injecting data into the stream. Also, with the readers, it is possible that they could crash before the reader gets an opportunity to checkpoint. So that means that there are going to be duplicate events. And so in order to perform joins accurately, it's really important to guarantee that we process every record exactly once. Also, we wanted to minimize the end-to-end latency from the time when we capture an event to when it's actually available for consumption by our customers. And the last challenge is to be able to be robust to delays between the arrival time of correlated events. In ad tech, what happens sometimes is that people load a website, but they don't click on the ad like till 2 or 3 hours later. So this means that the correlated event, which is, click is correlated to an impression, which is correlated to the bid, happen at sort of like there's a lot of delay between when these events actually happen. And building a system that's robust to the large delay between the arrival of the correlated events is a really hard problem. Because this directly translates into how much state you want to store in memory or somewhere else to be able to do the joins effectively. And our solution makes use of Redshift under the hood to do the joins. So we make use of our streaming message hub that collects data for different event types and then puts them into files on S3. We make use of data pipeline, which is an AWS managed service for picking up these files from S3 and then injecting them into a data warehouse such as Redshift. And then we end up having separate tables for each event type in Redshift, and we make use of the auction key as the primary key for each one of this table. And if you recollect, the auction ID was also the partition key that we used in our streams. We have two modes in which we operate these joins. We have a fast path in which the events are joined within 15 minutes and made available to the customer, but it's inaccurate because sometimes you will miss correlated events which might appear a little bit later. We also have a slow path, which makes data available full 24 hours after the event has occurred, but this is more accurate because we have a larger window over which we could run our joins. So in terms of trade-offs, one of the things that I'd like to point out is that our solution for joins is not truly streaming. We are in fact batching data in 15-minute chunks and then uploading it into Redshift. And this 15-minute interval is currently dictated mainly by limitation of AWS pipeline as to how often you can have recurring pipelines be scheduled. And we can easily work around that by moving to Lambda. But the other sort of issue I feel with our approach is that once data gets into Redshift, it's not easy to take it out of Redshift and stream it to a destination. It's possible to have data from the Redshift be unloaded into files in S3 and then set up a Lambda that sort of writes into Kinesis, but all of that is expensive and really doesn't feel correct. And so that, I feel, currently is one of the issues with our current approach. However, I do want to point out that our current approach scales really well. It's fully managed by AWS, and it supports many of our use cases. So now looking into the future, we are looking at what are the different alternatives that we could explore for performing stream joins. And currently, I feel there are a couple of options that are interesting. One is to use Spark streaming on top of EMR, or the other one, which was recently announced by the Kinesis team, is to use Kinesis Analytics. So here are some of my early thoughts on this. The advantage of Spark is that it can do any arbitrary data format or transformation. You're basically running your own code. However, from an operational standpoint, it's not clear how much of an overhead it would be to really run your own Spark cluster. It seems like it might be a big overhead. The advantage of using Kinesis Analytics is that it provides a SQL-like interface to streams, and our joins could basically simply be expressed as an SQL-like query. And also, since it's managed by AWS and it's elastic, you don't have to worry about issues such as capacity planning, et cetera. However, it's pretty early stages in terms of evaluating Kinesis Analytics for us. So we really want to make sure if it can scale to RTB-like workloads and support arbitrary data format transformations, et cetera, before we jump onto it. And so therefore, to conclude my talk, in summary, I talked about why building RTB applications is really challenging, and how by using the Beeswax bidder as a service, it's really easy for customers to build custom bidders on our platform. We use Kinesis as our infrastructure under the hood for all our streaming data needs. And in our application, we solved some of the key challenges that we faced, and I discussed some of the trade-offs that we considered. So one point I want to make, the final point here, is that the Beeswax platform is optimized for RTB. All the decisions that we arrived at after looking at the trade-offs were really with RTB in our mind, and it's possible that based on your application, you might arrive at different conclusions when you're looking at the same set of trade-offs. So that concludes my presentation. Thank you very much, and open it up for questions.